September 12, 2025. Astronomers detect the impossible. A colossal object streaking in from deep space, its tail spanning 5 times the width of a full moon, dwarfing any comet since Oumuamua. Within hours, a second visitor is confirmed, racing toward the Sun from an entirely different corner of the sky. The odds of this cosmic double arrival are, in the words of experts, astronomical. Officially, they're twin comets. But the evidence suggests something engineered. A mystery object entering our solar system with a purpose no one can explain. The story begins here. On September 12, 2025, the SH spacecraft's SWAN instrument captures something that freezes astronomers in their tracks, a blazing object slicing through the solar system. Early data reveals a tail stretching 2.5D across the sky, 5 times the width of a full moon, a scale unseen in modern comet records. Photometry pegs it at magnitude 7.4, bright enough for backyard telescopes and binoculars. The news spreads like wildfire, and amateur astronomers worldwide scramble to confirm the sighting. Just 2 days later, an Australian observer captures a stunning image. A streak of light so vast it nearly spills out of the camera's frame. By September 13th, the International Astronomical Union names the object C-2025R2, dubbed SWAN, after the instrument that spotted it. Within days, professional and amateur communities are fixated, sharing images and brightness data across hemispheres. SWAN's sheer size and luminosity spark disbelief. Unlike most modern comets, faint and reserved for powerful telescopes, SWAN is visible to anyone with clear skies and a sense of where to look. Its tail carves through Virgo, growing brighter as it nears the Sun. This isn't just another icy wanderer from the outer reaches. The numbers don't align with any recent precedent. SWAN dominates the inner solar system in a way not seen since Hale-Bopp, or perhaps ever. The amateur community, often the first to notice subtle changes, debates what could drive a tail this vivid. For now, SWAN is too big, too bright, and too fast to dismiss. As telescopes track its path, the question shifts from what it is to why it's here, and whether its arrival signals a larger, stranger puzzle. But SWAN isn't alone. Just days before its discovery, another object, 3I Atlas, was already inbound from Sagittarius, while SWAN traces back through Aquarius. On a star map, their origins lie over a quarter of the celestial sphere apart. Yet both are set to reach perihelion, their closest approach to the Sun, within a 10-day window. SWAN's closest pass is October 20th at 150 million kilometers. Atlas arrives October 17th, skimming the Sun at 203 million kilometers. Their perihelia are just 50 million kilometers apart, closer than Mars ever gets to Earth. The geometry is striking. Both objects follow steeply inclined orbits, with SWAN tilted over 60 degrees out from the ecliptic and Atlas nearly perpendicular to the planetary plane. The odds of two such objects, from such distant origins, converging on the Sun at nearly the same time and distance are vanishingly small. Long-period comets and interstellar objects typically arrive randomly, their perihelia scattered across years. Yet the decade's brightest newcomers are synchronized, entering a cosmic corridor, a narrow window in space and time. Complicating matters, Earth's telescopes face a blackout from October 8 to 18, when the Sun's glare blocks direct observation. This blackout cloaks the critical moment when SWAN and Atlas are closest to the Sun and each other, leaving ground-based observers blind to any unusual behavior. The timing, geometry, and blackout defy chance, raising a question: is this a cosmic coincidence, a hidden link, or something engineered? 3I Atlas breaks the rules from the start. Early spectrographs from the Atlas Spec Lab reveal a nickel-dominated body with virtually no iron, a composition unheard of in comets, which typically show iron-nickel blends. The claim sparks controversy, with labs demanding data rechecks and forums buzzing with debate. Further measurements deepen the mystery. Atlas's coma emits carbon dioxide at 5 times the rate of water, a 4.3 micron CO2 line dominating spectra while H2O barely registers. This is rare but not impossible for cold origin comets. What defies explanation is the tail's behavior. Observers note 3 distinct accelerations, each 2 weeks apart, July 29th, August 14th, and beyond, coinciding with sharp changes in tail color. Photometric data shows brightness spikes and spectral shifts from reddish to neutral and back. These delta V pulses aren't gradual like solar heated outgassing, they're sudden like thruster firings. Skeptics cite calibration errors, but the Atlas team, backed by data from the Abero Tracker Network and Bill Gray's telescope array, insists the pulses are real. The CO2 mix in the tail seems to modulate with each acceleration, a phenomenon dubbed thrust mix modulation. Energy estimates are staggering. If real, these accelerations require a 10 gigawatt power source, equivalent to 10 nuclear plants, far beyond any natural comet nucleus. The mainstream view leans toward natural explanations, but the nickel-heavy spectrum and stepwise accelerations keep the engineered object hypothesis alive. Atlas's anomaly file grows with each dataset, fueling both skepticism and speculation. C2025 R2C Swan stands in a class of its own. Its tail spans 2.5 dos. Its brightness rivals the greatest comets of the past century, and its core may output 10,000 gigawatts, more than Earth's entire power grid. Fringe claims push the boundaries further, suggesting Swan is armored, shielded, and powered in ways that challenge physics. Reflectance data shows a metallic signature, possibly a nickel-cobalt blend, materials used on Earth for strength and corrosion resistance. The term nickel-cobalt hull spreads through forums and podcasts, fueled by Swan's refusal to dim or fragment near the sun. A persistent silvery halo around the nucleus, shifting in pattern and intensity, hints at a plasma envelope, an electromagnetic shield against solar wind and debris. This earns Swan the nickname Fortress. Unlike Atlas's agile drone-like behavior, Swan moves like a tank, slow, steady, and seemingly indestructible. Its tail pulses with microthrusts, defying simple outgassing models. Photometric analysis reveals rhythmic brightness blips, suggesting precise course corrections via plasma bursts. Swan's orbit adds another layer, a 22,554-year cycle, reaching back to the last ice age. If engineered, it's been on this path since before human civilization began. Its arrival, synchronized with Atlas in the same solar corridor during a blackout window, pushes the odds of coincidence to the brink. Swan's luminosity, possible shielding, and immense energy output rewrite the rules, opening the door to theories once confined to science fiction. The synchronized arrival of Swan and Atlas, on a 22,554-year orbit and a possible interstellar trajectory, drops the odds of chance to near zero. Their timing, geometry, and blackout window fuel mission theories. One scenario posits a routine operation. The Sun as a cosmic pit stop for recharging or data exchange, leveraging solar energy or magnetic fields. Earth's own missions use solar flybys for gravitational assists. For probes, the Sun is a logical hub. A darker theory suggests an intervention, a rendezvous to recover or neutralize a malfunctioning unit, or a contest between rival factions over a resource. The energy reserves, 10 gigawatts for Atlas, 10,000 for Swan, imply active maneuvering, not passive drifting. Atlas's stepwise accelerations and Swan's microthrusts suggest mission-like control. Another possibility ties to Earth's radio transmissions. Oumuamua in 2017, Atlas, and now Swan could be escalating responses, an audit chain of increasingly complex probes sent to investigate or initiate contact. In each scenario, the Sun is more than a backdrop. It's the beacon, the power node, the rendezvous point. The question isn't just what these objects are, but what they're here to do. Swan's 22,554-year orbit aligns with the end of the last ice age, when glaciers retreated and human civilization took root. Ice cores from Greenland and Antarctica preserve dust and chemical shifts from that era, hinting at dramatic sky events, possibly bright comets. At Göbekli Tepe, an 11,000-year-old site in Turkey, stone pillars bear carvings some interpret as celestial paths, perhaps even comets. A few theorists argue these mark cycles like swans, though mainstream scholars call this speculative, noting no direct evidence links the site to specific astronomical events. Still, the timing intrigues. Swan's last pass would have coincided with humanity's first steps toward monument building and skywatching. Coincidence or not, it weaves these visitors into our origin story. From October 8 to 18, a blackout halts major observatories. Internal memos from US Space Command and the European Space Agency order teams to suspend radar and high-resolution imaging of Swan and Atlas. Data requests are delayed or rerouted. Public statements are barred until after perihelion. The silence is deafening, leaving only independent astronomers and amateur networks to act. Veteran tracker Bill Gray rallies a global web of backyard observers and small observatories. His call echoes across forums and encrypted chats. Keep your scopes on the sky, log every flicker, share the data before it's gone. The Abero Tracker Collective pools wide-field sensor feeds, while leaks hint at plans to bypass the blackout with radio telescopes and repurposed weather satellites. With official channels muted, this grassroots effort becomes the last line of defense against an information void. Anyone with a telescope or open-source software can join. The blackout isn't just a challenge, it's a call to action. When Swan and Atlas emerge from the sun's glare, the first clues may come from a backyard, not a government lab. Two anomalous objects have entered our solar system, defying all odds and raising questions no agency will answer. The search for truth is now in your hands.